Now, like I said, these next few modules are going to be very rapid fire. They're going to be, about one a week on average. Some of them will take a little bit longer than others. They kind of bleed together. So the lines between module 7 and 8 and module 8 and 9 are a little bit fuzzy because the concepts do build over each other. But what we want to focus on for today is starting to build some of our vocabulary and starting to use some of our vocabulary, use some of the concepts, tie it to things that we already kind of have somewhat of an understanding for, so that when we get to the stuff that is a little bit more new, especially Wednesday and into Friday, that we have at least some context for what those words mean. So we're going to start here with some terms that you should actually know already. We talked about the concept of a core electron and a valence electron all the way back in module 3 when we brought up the idea of electron configurations. If you don't remember the difference, what I want you to think about is, what is the difference between a noble gas configuration and a complete configuration? Because if you remember the noble gas configuration, we basically said, okay, hey, look, all of these electrons in this atom, they don't do anything. They're just there. And so if I know the configuration of krypton, let me focus on the stuff that isn't part of krypton's configuration. Those inner shell electrons, those are our core electrons. They're the ones that are in the interior shells of the atom. Those are the ones that primarily serve the purpose of shielding. So if you don't remember shielding, think about your periodic trends. What's keeping the nucleus from those outer electrons way out there? Well, the thing that's keeping the nucleus from the outer electrons primarily is the inner electrons. The fact that they put physical distance and other charge in between the nucleus and those outer electrons. So those are the core electrons. They're in the inner shells. Primary job is shielding. They don't do much else. They definitely don't participate in chemical reactions. On the other hand, we have what are called the valence electrons. These valence electrons, their primary purpose is they exist on the outermost energy level. So again, if we use the idea of this classroom as a model of the atom, if my desk here is the nucleus, the valence electrons would be those electrons the furthest energy level out, which would be the back row. And as far as the back row is concerned, they can move around, they can do kind of whatever they want. I'm so far away from them, I really can't control what they do. Well, from an atomic standpoint, that's where chemical reactions take place. Chemical reactions take place because those outer electrons, which are free to kind of mingle and interact with other atoms, well, they mingle and interact with other atoms. And as a result of those things, they bond. They create chemical bonds. Now, chemical bonding, or just plain old bonding, this is the result of what is called an electrostatic attraction. Electrostatic attraction here we're looking at the attraction that naturally exists between positive and negative charges between atoms. That's what we're looking at here. Now, there are different types of bonds that are made, and the type of positive to negative interaction changes, but regardless of what type of bonding we look at, we're always looking at this positive to negative interaction, and that's what draws these atoms together as they make molecules, as they make compounds. So let's look at the three different types of chemical bonds. Now, we were already aware of two of them. We went through nomenclature. We talked about ionic nomenclature and covalent nomenclature. Ionic nomenclature for ionic compounds. Ionic compounds feature ionic bonds. These are chemical bonds that result from an electrostatic attraction between a positive ion and a negative ion. Positive ion we call a cation. Negative ion we call an anion. But we've got two different charged ions, and we know that opposite charges attract. That's what puts them together. That's what creates that bond for us. The other kind of bond that we are most familiar with is the covalent bond. This is the bond that is used to make molecules and molecular substances, polyatomic ions. These are the bonds that are formed as the result of the sharing of valence electrons. And so where does that electrostatic attraction come in? Well, we don't have ions this time. We don't have positive ion to attract negative ion. What we have is positive nucleus attracting negative electrons from different atoms. Now, as you might expect, the covalent bond is going to be necessarily weaker than the ionic bond because there's no way that that attraction can be nearly as strong. In an ionic compound, I've got a positive and a negative, and they're right next to each other and touching each other. So I've got two things at play here. I've got close proximity and I've got charge leading this bond. And so as a result, ionic bonds tend to be pretty strong bonds. In a covalent bond, I've got the nucleus, which is positively charged, and I've got these electrons in this other atom that are attracting and being attracted to that nucleus. So I've got a little bit of different thing. Charge-wise, probably not that different. Distance-wise, a lot different. They're not touching each other. Those electrons in that other atom are a little bit further away than right next to the nucleus. And so as a result of that, the bonding that exists in covalent compounds isn't nearly as strong. Now, thanks to thermochemistry, we have a way that we could actually quantify that. We could quantify the energy of a bond, a covalent bond, versus the energy of an ionic bond. We saw bond enthalpies for covalence, just as recently as Friday. For ionic compounds, that's called lattice energy, and it's kind of the same principle, but a lot bigger, a lot bigger. The third type of bond is something called a metallic bond. Now, metallic bonds take this whole idea of sharing electrons and they ramp it up to the nth degree. Basically, we can think of a metal sample as a very close, interactive, compact group of atoms arranged in a very ordered, very neat array where every single one of those metals has donated their valence electrons for the good and betterment of the collective whole. And so to kind of wrap our heads around what that looks like, what that is, instead of I've got one atom that has donated one electron to another atom, and they are now brought together. Instead of that, I've got a mole's worth of atoms. So 6.022 times 10 to the 23rd, donating at least 2 electrons each to the collective sample as a whole. So 2 times Avogadro's number of electrons for every 1 mole of atoms. So I've got kind of the best of both worlds here. All of those atoms in the metal sample, because it's a solid, they're all super close together, very highly associated with each other. And there are tons, and I mean tons, of electrons floating around in what we call the sea of electrons that allow each of those metal atoms to be associated with all of the other metal atoms. For this reason, we don't just get one attraction. We don't get 2 attractions. We get lots of attractions. Those metal atoms are very, very, very well associated with each other. And because they are so well associated with each other, the properties that we generally think of as metallic become a lot more kind of sense-oriented. Because now we can see, okay, all of those atoms are really closely associated with one another. So when I hit a metal with a hammer, the metal adjusts. It's flexible because those atoms are so well connected to each other that so long as I don't sever the connection completely, they're going to stay associated with each other. They're just going to get thinner and thinner and thinner and thinner until eventually we'll get it so that they're 1 atom thick, and then it becomes a lot easier to separate them because any force, there's nowhere else for that to go. Electrical conductivity makes sense now. Remember, electrical conductivity is all about the movement of electrons. Well, I've got free electrons in spades here in a metallic compound. So those electrons can move around easily, conduct electrical current easily. So from a comparison standpoint, this is the primary advantage. This is why metals have the properties that they do. Each one of those copper atoms touches at least 6 other coppers. Depending upon the size of the atom and the crystal shape, they could touch as many as 12 other atoms. Whereas this potassium ion probably is only touching 4 chlorides, maybe 6. Certainly not any more than that. And there's only a 1 electron transfer being shared here. Not what we were talking about. So those kinds of differences, are significant. That's why ionic compounds can do some things that metals can, but other things that they cannot. And that's why covalent compounds have very different properties from either of them. So we move from kind of this overarching theme, which is just some general vocabulary about different compounds, So we're going to start to get into some explanations for why compounds form, and is there some rhyme or reason to how they do what they do? And the answer there is yes, obviously. So we need to bring in this concept known as Lewis theory. Lewis theory, proposed by Gilbert Lewis, says that the whole point of bonding is for atoms to get to a noble gas electron configuration. So the primary theory that was posited by Lewis is that the noble gases are unreactive. And they're unreactive because they already have all of the electrons that they need. They have no need to transfer electrons or share electrons because they're already good where they are. And so the question becomes, how do other elemental samples get to that stability so that they too can have the same stability as those noble gases? And here's where we enter the octet rule. With the exception of helium, every single noble gas has 8 valence electrons. 8 octet rule. So the whole purpose of bonding is to take however many valence electrons I have and turn that into 8 valence electrons one way or the other. And so there are 3 primary ways that you can go there. You can gain electrons, you can lose electrons, or you can share electrons. Now, the first 2 processes, gaining or losing, that's going to involve the formation of an ion. Because if I'm gaining electrons or losing electrons, it's going to put my balance of protons and electrons out of balance. And I'm going to have more of one than the other, which means it's no longer going to be a neutral atom. It's going to be some kind of ion. Sharing electrons doesn't actually change the total count of the given element, but it does provide extra electrons that can be used to fill that particular atom's octet. And so we don't see a change in ion or character, but we do see a change in the number of electrons that that atom is associated with. So that's the octet rule. Now, to help us get to that octet, we often will use something called Lewis dot notation. Now, Lewis dot notation is very easy to use. Basically, what we are doing is we are turning that electron configuration into a number of dots around that elemental symbol. But we can actually be a little bit more sneaky than having to write out the electron configuration each time. I don't need to actually do that. And the reason I don't need to do that is because these configurations are periodic. So if I'm looking at the alkali metals, this is group 1. Group 1 has 1 valence electron. If I'm looking at the alkaline earths, this is group 2. Group 2, 2 valence electrons. For the boron group, the periodic tables that we use call this group 13. There are some periodic tables, including ones in your book, that will call this in addition to group 13. They will refer to it as 3A. That's something called the CAS numbering system. We don't spend a whole lot of time talking about the CAS numbering system because aside from this use, this is really the only place where we would actually use that numbering. Carbon group is group 14, or like I said, sometimes your book refers to it as 4A. And so we can see that there is a pattern here. And that pattern is that if we kind of ignore the fact that the noble gases, or excuse me, that the transition metals exist, the group number is the number of valence electrons. Now again, for the 13 through 18, we just take the 10 off of it because that 10 represents the 10 groups of transition metals in the middle. And we really don't do Lewis dots for transition metals. Valence character for transition metals is a little bit complicated and well beyond what we're trying to get after here. Now, what do these tell us? Well, they tell us a couple of things. First of all, they tell us how many electrons we have. So from here, I can look at this and say, oh, okay, fluorine. Fluorine has 7 valence electrons. There are 3 ways to get to 8. It could lose all 7. It could gain 1, or it could share 1. And so of those 3 options, what are the most likely? Well, it's not the lose 7. It can gain 1. If it gains 1, it goes from F to F negative 1, which we know halogens tend to take on -1 charges. Or it shares an electron, and when it shares an electron, it's going to make 1 covalent bond to turn that 7 into 8. Easy enough. I can look at something like the nitrogen group. 5 valence electrons. My options are I lose all 5, I add 3, or I share 3. Of those 3 options, the losing 5 is pretty much out. I'm either going to add 3, -3 charge, or I'm going to share 3 and make 3 covalent bonds. So from a Lewis structure, I get an idea of not only what is the most common type of ion that it makes, but also if it does participate in covalent bonding, how's it going to do it? How many bonds would we expect it to make? And so from that, we can see why carbon and silicon, we didn't really talk about them in terms of ionic character. I've got 4 valence electrons. My best options, add 4, lose 4, or share 4. From an energetic standpoint, adding 4 or losing 4, neither of those options are all that great. Sharing 4, that's a lot easier to do. How does it share 4? It makes 4 covalent bonds. Now it's just a matter of figuring out how to get 4 partners for it. All right, let's do a review question here. We're looking for selenium, Se. How many valence electrons are in selenium? How many dots should I put around that selenium symbol? Answer it here. All right, CT. What's the answer here? 6. Yeah, how do you know that? Yeah. So selenium is in the same group as oxygen and sulfur. So this is a version of the periodic table that your textbook shows. And so you can see you've got both the international system, the 1 through 18 system that we use. It also is showing 6A both as Roman numeral or as Arabic 6A. Either way is fine. And that's all that does is it just shows you how many valence electrons there are. Like I said, the B system, the CAS system, we don't really get into too much. There isn't a whole lot of help for us there other than in this particular circumstance. All right. The other big concept that we want to talk about today is electronegativity. Now, electronegativity concerns specifically what happens when an atom bonds. And what we want to think about in that kind of context is the idea of, are those electrons actually being shared evenly by the atoms that are in that bond? So this is not a model of the atom, but we're going to use it to kind of illustrate here. Let's imagine that we have a chemical bond between these two blue spheres here. Let's just imagine that these are the two nuclei that are bonding. Well, in this particular scenario, we could have even sharing of electrons, where we can see that the electrons are very evenly distributed between one atom and the other. Or we could have uneven sharing, where it's clear that the electrons are much more on one side than the other. How we know the difference is through something called electronegativity. Electronegativity tells us how well does one atom draw electrons to itself when it bonds. Now, there are a lot of factors that go into electronegativity, but the primary one or two have to do with what kinds of charges does it usually make. The ones that are negative tend to be more electronegative. The ones that are positive tend to be less electronegative. And how big is it? The bigger the atom is, the more that charge kind of gets dispersed, the less drawing power it has. So with those two factors in mind, the things that would be the most electronegative would be the smallest atoms that have negative charges or tend toward negative charges. And so for that reason, we would look at fluorine, which is of the bonding elements in period number 2, it's the smallest. If you remember our periodic trends, the periodic trends tell us as we go across the table from left to right, they all get smaller because the number of energy levels hasn't changed, but the number of protons has. More protons means more drawing power, and if the energy shell hasn't grown any, hasn't gotten any further away, then the existing electrons are going to get pulled in more tightly. So fluorine has kind of both. It's small, and we know it's negative. Closely related to that, oxygen, small and negative. Nitrogen, small and negative. Chlorine, negative, not as small. So our general trend here with electronegativity is as we go toward fluorine on the periodic table, we tend to see more electronegative elements. As we go away from fluorine toward francium, we tend to see less electronegative elements. Now, the Pauling scale here does attach value to each and every element. And where that is useful to us is it helps us to kind of figure out what kinds of bonds might be made. And we can do so using something called electronegativity difference. So I'll come back to that one here in a second. If I'm looking at two atoms that make up a bond, the difference in their electronegativities tells us something about the bond that they create. If the electronegativity difference is relatively low, anything less than 0.5, we can pretty safely consider that the electrons in that bond are being shared relatively evenly, and we would call that bond nonpolar. If the electronegativity is greater than 2, we have such a stark difference in electronegativity that not only are the electrons kind of being unevenly shared, we can almost think of that electron as having moved. So here's where we get into the redox part of the conversation, where is the sharing so uneven that we actually think about the electron as having been transferred from the less electronegative to the more electronegative element. When that's the case, we're talking about ionic bonding in that circumstance. Covalent is kind of in the middle, polar covalent, where we've got enough of an electronegativity difference that we can see that there is an unevenness in the sharing of electrons, but it's not to the point of transfer yet. So electronegativity differences between 0.5 and 2, that's our polar zone. Now, one really important thing that we want to pull off of this, these distinctions run together. We're presenting them as kind of being these stark differences, but reality is they kind of blur a little bit together. Things that we consider to be ionic compounds may not necessarily have ionic electronegativity differences. And that's where the chemistry behind them actually can get really, really interesting. Now, we can use color maps like these to help show some of that electronegativity difference, to help show some of that polarity. So here we have fluorine. This is a homonuclear bond. We've got the same nucleus, the same element on both sides of that bond. What do we see here? Well, we see that because the two are the same atom, they have the same affinity for the two electrons that they're sharing. And so there is no tug of war going on between them. They both are evenly interested in those electrons. The net result, I've got a distribution map here that shows no favoritism on one side or the other. So the way to read these color charts is they are like temperature maps. If you see hot colors, reds and oranges, that shows that the electrons are kind of hanging out in those locations more often. If you see cooler colors, greens and blues, that tells you that the electrons are kind of not hanging out there that much. And the kind of yellows and oranges in between are, well, you guessed it, in between. So for fluorine, F2, we see very even distribution. Yes, there are some red zones or some oranger zones, but they're diffuse. We've got one on each side. Chlorine monofluoride, on the other hand, ClF, we can see that there's a distinct difference here. Red around the fluorine, kind of yellow and orange and green around the chlorine. Why? We know that fluorine's more electronegative. So the electrons are going to be pulled this way toward the fluorine because of its higher electronegativity. And that's going to create a distortion where the electrons are going to be spending more time on the one side than on the other. And that has more significant implications as we start getting into module 8, when we start looking at not just bond polarity, but molecular polarity. And does a molecule actually have an uneven distribution of electrons or not? All right, so let's close up today with a quick question here. This is a ranking question. I've got 4 bonds. They're all hydrogen to something else. Which of these bonds would be the most polar and which would be the least polar? And so kind of put them in order from there. So the way to think about this, everything's being paired up with hydrogen. So hydrogen's kind of the control factor here. We know that as we go toward the right of the periodic table, we're getting more and more electronegative. So regardless of what hydrogen is, we know that hydrogen plus the most electronegative element is going to give us the most polar bond. So HF, since fluorine is the most electronegative element, that's going to be the most polar bond. From there, we're just going to go in order from right to left as we encounter each of these. So hydrogen to oxygen would be next, then hydrogen to nitrogen, then hydrogen to boron, since boron would be the furthest left and the least electronegative of these 4 elements. So get a chance to do a little bit more with this on Wednesday. On your way out today, make sure that you hit the stoplight question here and read through, go ahead and do this assignment 7-1. Get us ready for molecule drawing on Wednesday. It'll go a long way to kind of making that transition a lot smoother. Have a great day.